Yeah, it's really because I thought that on the canvas there is no announcement that there is lectures on. There no lecture at 11. No. Okay, yeah. I'll make announcement, but next week will be Thanksgiving anyway. Okay, so I'll switch it on. Okay, so let's just continue what we were doing. This last two lectures about quantum information. So this whole course is about that you look at different subjects and you try to look at it from the viewpoint of entropy. And entropy, classical entropy, is something which quantifies the total number of possibilities of microstates of unknown to you variables which are compatible with a given observable macroscopic state. That's a classical entropy. What we'll introduce today is something which has no classical analog. It would be called entanglement entropy, and it will be related not to the number of microstates, but to the number of outside states. So we'll have a system, and what we find out that in a quantum world you can never really isolate the system because of the phenomenon which we'll call entanglement. Okay, so that's more or less the subject of today's lecture. But first, let me remind you what is the quantum mechanics. You all had some course on quantum mechanics, right? So mathematically, it's a totally trivial science. It's just a linear algebra. So we say that our system can be characterized that they are in a state. A state is a vector. Good. And so this vector can evolve. Also, it can be in a superposition of different vectors. And this is something which is does not have any classical analog. Because we also have operators which correspond to observable. For example, we have observable, which is the momentum of a particle. And this operator, you can think about it as a matrix. It's something which acts on a state. And we can classify our states, for example, by eigenstates of this operator. And for example, we can classify our states as eigenstates of the energy operator or Hamiltonian operator. And all these states have different energy. And in a classical world, the system can have only one energy. In a quantum world, it can be in a superposition of different states, so you can have different energies simultaneously. And it is realized through measurements. And this is another thing which is totally different from a classical world, namely that every time we make a measurement, it's a very specific procedure. It immediately collapses the whole set of possibilities into one possibility. So even when my system exists in a superposition of state, so potentially it has many different energy, any measurement gives a definite energy, which means that it projects all the superposition into one state. If I'll continue doing this measurement after the first measurement with the same system, it will give the same answer. Namely, I collapse. There is no other. These possibilities are already unrealized. But if I prepare identical set of systems, and each one is in a superposition, and I will be doing measurement of energy to all of them, then I will find out that I will obtain different energies. And this different energy will come with different frequencies or probabilities related to what is the fraction of this measure. Okay? And this possibility to exist simultaneously in many states is one thing which makes this quantum mechanics practically interesting for, let's say, computation. You may hope to do your computation in parallel because you have many states involved. But there is another property of quantum world which is no less strange. It's a non-locality. And this non-locality is expressed in terms of non-commutativity of the operators. So for any observable, I have an operator, which could be thought of as some kind of Hermitian matrix. And it could be that these matrices do not commute, because matrices generally do not commute. And if these matrices do not commute, that means that we cannot have a definite value of one observable and another observable at the same time. And this is it's very interesting how it was painfully understood, and Pauli and Heisenberg wrote each other letters like almost every week. And in one letter, Pauli said that if you look by one eye, it's kind of very, very clear picture. By another eye, it's a very, very sharp picture. But if you open both eyes, it's very blurred. This is essentially this message. So technically, it means the following, that if I have, let's say, two operators, A and B, and I consider commutator, which is by definition is, let me make matrices will be with heads. So it's AB minus BA, right? And I would project, and I would compute, how I would call it, psi probably. So I would do a measurement, projecting it on some state psi, and I would compute square root of it, right? And now, of course, I can add to it AB plus BA, right? And that would be, this would cancel, and that would be 2, and in a square it will be 4. So I can write that this is a 4 psi AB psi modulus squared plus this symmetric, well, minus this symmetric combination AB plus BA squared, which means that this quantity is always less than this. So I may write it like this. But this is, again, by Cauchy-Schwarz. I can write as A squared times B squared. So I can write that this is less than 4 psi A psi squared psi B psi squared. And so this is essentially a statement that you have a variance of this times variance of this, and it's restricted from below by the value of the commutator. So if they do not commute, you cannot make these variances simultaneously arbitrarily small. And in particularly, as we all learned in undergraduate version of quantum mechanics, is you have pi, which is in X representation is this operator, then Px commutator is H, which tells us that the sigma of pi times sigma of X, right, like this, must be larger or equal than H over 2, right, square root. That's an undergrad version of uncertainty relation. What I want to show you today is a graduate version of uncertainty relation. And it's like, you remember that second law, we had this delta S larger or equal than 0. That was the undergrad version of a second law of thermodynamics. And then we derived more sophisticated version, for example, exponent of delta S mean value equal to unity. So this follows from this, but this is a more powerful version. So today we'll derive a more general version. But again, as I promised, what we'll do today is we'll look at everything from the viewpoint of entropy. And on the second thought, it's strange why it kind of took such a long time. Very much advise you, if you never did it, to read original Planck paper. First of all, it's very clearly written. And you remember the problem. They had this spectral distribution of radiation, and they were looking at low frequency limit, and it was like power law, and then they looked at the high frequency limit, and it was some exponent. And they were kind of trying to find where you can actually get one or another. And what Planck did, he wrote an entropy of this distribution. And he essentially, and you can make an entropy for this part, and you can make an entropy of that part, and he just took it as a sum. What he got, just looking into it, was a binomial distribution. How many ways to distribute a finite number of quanta. He actually hated it. It's interesting. He was a thermodynamicist, and that's what Boltzmann stuff. Boltzmann would try to sneak this probability, all this kind of randomness into physics, and he actually disliked it, but it worked. Okay, so essentially, quantum mechanics started as from the entropy. So if we look here, we say that this is essentially a statement about variances. It quantifies the joint degree of uncertainty in the distribution of P and the distribution of X. Of course, if you have a free quantum particle, you remember that its probability distribution is exponent minus x, well, minus some x mean squared divided by some, I don't know, variance, sigma x. For Gaussian distribution, variance is the right value of uncertainty. And the same, if you Fourier transform it, you get a momentum distribution. So free particle has a Gaussian distribution, but general distributions are non-Gaussian. So at some point, surprisingly late, people started to ask what would be the analog of it for non-Gaussian distribution, for non-free particles, for interacting particles, for more complicated system. And then you kind of, you technically can kind of divide it by square root of h, square root of h, and over 2, take a log of it. And because you probably remember that the entropy of a Gaussian distribution is a logarithm. So for Gaussian distribution, it is identically the statement that S of p plus log S of x larger or equal to 0, right? Because this is the log of sigma p square root of h plus, of course, you need to somehow normalize p and x at the same units, or you just can normalize them different, whatever you want, because this normalization factor will cancel from this sum of two logarithms. Sigma x divided by square root of h over 2 larger than 0. Okay, so this is, and that was realized pretty late at 80s, 60 years after Planck. This is the most general form of this uncertainty relation. And then you can look at it in a little bit more formally. So you can say, imagine that I have an orthonormal set of states, let's say x1, yeah, by the way, if I am in d dimensions, what I will get? In 3 dimensions, let's say. What would be the respective thing? So in 3 dimensions, I would have sigma p would be px squared plus py squared plus pz squared, right? So it will be 3 times sigma px, right? So what you would get here, you would get logarithm of 3 when you, because your sigmas, each one multiplies by 3, or by a general any dimensionality. So you can somehow make it a little bit more formal you can say that you have some basis x, orthonormal basis, and you have some other basis z. For example, in a simple case, you have, let's say, z1, and again, they all are orthonormal, all are unit vectors z2. So you can, in general, make your measurements which project on one basis or which project on another basis. Okay? So if you, for example, do your projection on the set x, that could be an uncertainty which would be S of x. But you can take the same operator and project it on the other set of states, which would be z states. So the general statement is that S of x plus S of z. I'll write it now, but I'll prove it maybe 40 minutes down the road, because I'll prove even more general form of it. And this is larger or equal than logarithm. By tradition, it's called 1 over c. And what is c? Is a maximum over x and z of a projection x, z modulus squared. What I mean by this projection, I mean this is the projection of z on x, right? And this is the projection on z of x, right? They could be different. They could be a little bit shifted one into another. Then this projection is large. Or they can be, and in particularly, these two different sets are called unbiased if x, z, let's say, for any I and for any k, for 1, for 2, they all equal squared, right? Yeah. Equal to 1 over d. It means that I have a orthonormal set of vectors, and another is just randomly turned with respect to it. So each vector taken out of xi just projects on all other vectors from z more or less uniformly, where d is the number of these vectors. In this case, d is equal to 2. Okay? And so this is a general relation, and particularly for unbiased state, we would have Sx plus S of z larger or equal than log d. Okay, and again, I'm not deriving it now. I just postpone it until we come to the. Now, entropies which we are using here is just familiar Shannon entropy. So we have some probabilities. For example, for a particle, we can define psi function, take modulus squared, say this is the probability of having particle at a position x, and compute mean p log p, which would give us the entropy of a Gaussian distribution. So this is a pretty familiar. Now, we would like to characterize something which would be not about a probability of measurement results, because this probability is a probability of a measurement to find particle in the position x. But we would like now to say something about states. These states which are behind this probability. So every time we do measurement, we collapse all this. Now we would like to somehow characterize the states, not the probabilities. And again, exactly like we did it for a bit, and the bit was a unity of information which corresponds to two possible outcomes, and it was an uncertainty related to two possible outcomes. We now consider a quantum possibility and the quantum system, which we would call qubit, which could be in two different states, and we call this 0 and 1. The quantum states, which means that the most general state of a qubit is something which is it's a superposition, right? A or B or alpha or beta, A or B, okay? So now this is the most general state of a qubit, and if we really want to take any measurement, which means that we would need to compute, take an operator O, which measures something, and then we need to take its matrix element A0 plus B1, well, complex conjugated, this is on the left part, A0 plus B1. Well, you all know this, I'm just remind you, because in a moment it will be very much different when we start talking about entanglement. So what we'll get here, we'll get this and this. This would give us A, well, this is A modulus squared O in between 0 plus B modulus squared and the matrix element of O in between 1s. And we also have A, B plus B, A. And this will be cross. Well, physically it corresponds to some probability of transition from state to state. But this is the most general expression for the expectation value of any measurable if we are in a superposition of states. So let's just remember it, and then we'll return to it and compare it with something else. So I want this to be preserved for posterity. Okay. Now, of course, what we need to require is that A squared plus B squared is equal to unity. Right? Our system is somewhere. Any measurement of it would find it in either 0 or 1. So this imposes one condition on two complex numbers. And we also may assume, and this is generally true, that the overall phase between A and B does not matter. But the relative phase matters, right? This is something which is A, B cosine of a relative phase. So what we essentially get, we get out of 4 numbers, we disregard the overall phase and we impose normalizability. So we have 2 numbers. One may say that we characterize qubit by 1 amplitude and 1 relative phase, or just by 2 amplitude, or whatever we wish. But essentially it means that the qubit state is characterized by a complex number, not a bit like a classical bit, a complex number. If you remember from a rate distortion theory, we discussed that just to represent a real number, you need infinite number of bits. To represent a complex number, you need twice infinite number of bits, right? So in principle, this is a huge information which is needed to specify this quantum state, this superposition, right? And unfortunately, what quantum mechanics tell us that we cannot really measure it. Any measurement would collapse it either to this with different probabilities. And which tells us again that measurement is something different. You remember in classical information theory, we say measurement are like messages. Now what we'll discover, and what this lecture is essentially about, is that we can not directly measure the state, but we can actually communicate it, and we can do something which lets us to learn about the state or to send it, which means that it's a meaningful question how much information is in a state, even though it's directly inaccessible. And the possibility that we have for manipulating the state, it means that we need to take something outside of it and use it to learn or to send or to manipulate a given state. And it brings this idea of entanglement. And again, it's something which is essentially a manifestation of a deep non-locality of a quantum world. Okay? So now let's discuss what we mean by that. So now let's consider two parts. Let's say that our world is divided into A and B. This is our world, and this is A, and this is B. And we assume that all this world is in some pure state, namely that it's not a superposition, there is no any randomness about it. It exists in some state. Let's call it psi AB. But we want only measure, or we're able to measure. This is our accessible part of the universe, or something which we have in our anyway, we can do measurements only on A. Okay? And so we would like to compute, again, psi AB, some operator which acts only on A, and it's essentially a unit operator acting on B. It does not act on B. On psi AB. That's what we would like to do. Of course, it depends on what is this psi. We can first simply and a little bit less formally to characterize, let's say that there are variables x over here and variables y over here. So the simplest possibility that we can consider is that psi AB is factorizable. So it's a psi A of x times psi B of y. Well, in this case, it's pretty easy. Then in this case, if this is true, then I would have that this is I would be in between psi B, and it gives me just unity because it's a pure normalization. So I would have psi A O psi A, namely that I can still characterize my psi I by a vector. This is a vector. Okay, this is a vector of a state. But it could be that this is not true, that psi AB is non-factorizable. This is the most general state where it's not factorizable, right? It's just that the way that you measure x also depends on what is actually in y. There's nothing so kind of so we say that if it's not factorized, then when you act here on this AB, you act only on x, right? Or acts on A or A of x. But it will change this, right? So I cannot say that I can do it as it characterized by a single vector. What I need to do is I need to introduce a matrix, and this is something like this. I take CA of x prime, and I AB and y, and I take psi of x and y with the same y, and I sum it over y, as we say, trace. I trace all y. This generally is dependent on x and x prime. Now, if I want to compute this, in this case, it would give me the thing that I need to take O, act on rho x prime x, but it's only on I act on x, on something which is on my this side, right? And after I do this, I need to put x prime equal to x. Okay? So essentially, it tells you that if you and now this is the sum over x. So this is something which is apparently tells me that if my psi function is not factorizable, then I need to characterize the state of the system A not by a vector. And in a moment, we'll see the meaning of it, because the system A is not in any definite state. It could be with different states. Let's now do it in a little bit more formal way. So what corresponds to this is, as they say, that psi A B is a tensor product. How I call it, psi AB is psi of A. The notation is like this. You familiar with this notation? What is the tensor product of two vectors? Everybody knows what is the tensor product. So if I have a vector A, B, tensor product with C, D, E, which length of this vector? It's a length 6. It's AC, BC, it's AD, BD, and it's AE, BE. Okay, so this is just a general definition. So what is actually I meant here is that I have such a tensor product, and if I put the it's over here, so my psi AB will be psi A, psi B, O of A, I of B, psi of A, psi of B. This is what would be factorization in this case, right? So now this would be, again, the O would be with this, the I would be with this, and I would get a usual expression. What is a generalization of it? Of course, this is not a most general form. The more general form if there is a sum. So I may assume that my psi AB is psi AI times psi BI and sum over I with some factors which I for now call square root of pi, and in a moment it will be clear while I'm doing this. Okay? So this is generally a sum of such tensorial product. This is a more general form. One can say that there could be even more general form of it, because in principle, if I have at my A system vectors from 1 to n, and my B I can have from 1 to, this is 1, psi A1, psi BM, right? And here will be psi B1. So I'll have a whole matrix, right, generally, which is psi AN, psi Bm. So one can say that such matrix is the most general state of a composite system, but then one can argue that this matrix generally, it's called Schmidt decomposition. I think that you also learned this algebraic notation. So it's generally M by N matrix. If N is larger than M, then you need to make it N by N, adding just zeros. And then you make a unitary transformation, rotating one M times M transformation, you rotate B, other N by N transformation, you rotate it, and you can make this matrix diagonal. So essentially, you'll bring it to this form, and you make it orthonormal, which means that you say that the sum of pi's is equal to unity. That would be, and notice that this Schmidt orthogonal decomposition, it's a procedure which makes it a single sum, not like here a double sum. So it's essentially just a diagonalization of a matrix, and still it's a sum. It is not a product. It's a sum of products, right? So the states of a system A and the states of system B are not factorizable. And if in this sum there is more than one term, this is called entanglement. That's a definition. Entanglement is the following statement. In this sum, more than one term, then A and B entangled. And the rest of the lecture will be an exploration of what it actually means, that entanglement. Okay? Now, if I now compute this expectation value of my operator, so what I will have? I would have a sum over square root of pi psi I A psi B I, my operator O acting on A, identity operator acting on B, well, IB, let's put it this way. And here I have another sum, this time over J. Right? This is just two sums, right? And it would have psi J A and psi J B. What is important that here is JJ, but generally these J's and those I are different, right? So now what I do, I take this I, it would work with these guys, and I take this O, and it works with these guys, right? So now what we'll find out is that this is a sum over ij psi a I O psi a j times psi a I 1 b or psi b psi b j. This is I. But identity operator is really diagonal, right? So this guy is delta ij, right? Because it's just a unity. Okay, so this is essentially, and I assumed that I'm working with a state which are orthonormal. So when I'm writing psi I, psi bi, psi bj, this is delta ij. This is an assumption of orthonormality. So now delta ij makes it out of a double sum a single sum. So what it tells me is that this is, and what I have missing here probably, yeah, square roots. Yeah, I forgot a square root of pi, and there was a square root of pj. So what is standing here is a square root of pi pj, right? Now with delta ij, it would give me sum over I, pi psi ai o psi ai. Okay? So I may say that this is a trace of O with a matrix rho, right? This is a sum of a diagonal elements, right? I goes from 1 to d elements, and matrix rho is something which I can write it as a psi I. It's a matrix. I think you know Dirac notations, and it comes with p i's. Okay, so this is and it's sum over I, right? So this is what is called density matrix. It's the same what we defined here, where it defines the density matrix. Yeah, this rho xx. This is similarly density matrix, and the same you can say that what I took my state psi ab and traced out b, and I finished with this matrix. So if I want to compute any expectation value, I need to take my operator, act on this matrix. It will be again matrix, and then take a trace out of it. Okay, that's a general. And so let me reiterate this important message. If you have a state, a quantum state, if you do quantum mechanics means that you are working with a closed system. It's characterized by a vector. If you are working with a system that has environment, but you can only measure this system, you can characterize it only by a matrix, not by a vector. In a simple technical term, it is that difference, right? It's not now a state of this. So what we call such a state, it's not a state in a quantum mechanical sense. We call it still the same name, but we add a qualifier. We call it mixed state. You can say that in a mixed state, my system is in a state I with a probability pi. The sum of pi is unity, right? So, and that's why we did it all orthonormal, but it's not a superposition of this state. Why? Because if you look at a superposition, the result of your measurement, any operator O, was sensitive whether this operator have a non-diagonal element. So it was sensitive with respect to your complex phases of A and B. Here, no such thing. If you do any measurement, you will see that it's only knows about these numbers, and they are real numbers. Right? The square root of pi's, the weights over here, they're all real numbers because all pi's are positive. Those are probabilities. Okay, so now we'll consider two-qubit system, and specifically would what is this matrix? First of all, it's non-negative. It's a Hermitian matrix. It's symmetric. It has a unit trace because the sum of all pi's is unity. So if you just take trace of rho itself, it will be equal to unity. And Landau, this PhD, by the way, this almost all the science that I described here was done by people who were doing his PhD. That was Landau's PhD. He was 19 when he wrote this paper, and kind of immediately they understood that this is kind of oh, okay. So now what I want to demonstrate you on a simple example, like here, that having A and B in a mixed state is not the same as being in superposition, and also introduce this so-called Einstein-Podolsky-Rosen states. So what now? Let's consider a very specific example of psi AB, which would be, again, made out of this sum, having more than one element, but on a simple example of a qubit. Okay? So let's say that both A is a qubit, could be in 0 at 1, and B is a qubit. And I consider, let me see which notation, A and B. Yeah, also A and B, like in this superposition. So let's say that I consider a state which is not generic state. Generically, I can have a state where A is 0 and B is 1, A is 0 and B is 0, etc. But I really kind of already, I don't want to consider this whole matrix. I really want to consider a very, very special combination, not a general state, and it will be like this. So this is A, this is B, and like this, which means that it's extremely correlated state. This is, and this tells you the following thing. You measure A, the B is the same. Okay? So they are perfectly correlated. There is no 0, 1, 1, 0 combinations over here. Okay? And now, if I take any operator acting on A, and I would compute expectation value. So it will be A 0, 0 plus B 1, 1. And here will be A, well, this complex conjugated. And here will be A 0, 0 plus B 1, 1. And of course, here will be identity operator acting on B. So what I will get here, you will see that I will get A modulus squared O 0, 0 plus B modulus squared. It's like this PIs over here. Just P1 is A squared, and B1 O 1. And it's totally insensitive whether there is such cross element. Okay? So that's the difference of being in a mixed state of a qubit. So my A is in a mixed state. And here is my qubit is in a superposition. And you see that they give you two different answers. So what is in this particular case, how would I describe the density matrix for, so this is a state. My system AB is in a quantum state. Now, what is the system A if I don't know system B? Apparently, this is a result of any measurement on A. You see that it gives you 0 with a probability A squared, and it gives you unity with a probability B squared. That's it. It means that our density matrix here is a diagonal matrix with A, B, 0, 0. Okay? So again, in this simple example, we see that if we want to characterize a one qubit out of a two qubit system, and this my 2-qubit system is in this very, very special state, right? So now, again, we may ask, what is the entropy of this distribution? Mixed state means that my system is either in one state or in another. This means that it's simultaneously in both states. Okay, this is two differences. But if now it has a probability distribution, then of course we may compute its usual entropy, which would be a Shannon entropy. And it's of course a squared log a squared plus minus b modulus squared log, well, b is 1 minus a squared, so it's like b squared. Okay? But now we want to introduce something which is related generally to the matrix, and it is the most important definition today. That would be an entanglement entropy. So what we now do, and to distinguish, I will still use S for all entropies, but every time I will be using entanglement entropy, it's also called von Neumann entropy. Von Neumann paper was done next year after Landau. I would be writing S of rho, right? So this was S of A. So there will always will be Latin for Shannon and Greek for von Neumann. Okay. So this is von Neumann entropy, and it's defined as a trace. It's a matrix, rho log. Well, it's in bits, so I will be always using rho log rho. Okay, that's a definition. Okay, it's a definition. It's minus. Okay, now it's a well, you know how to work with logarithm or exponent of a matrix. You can expand it, or you can, for diagonal matrices, it's just clear that you take a matrix which is diagonal, but on a diagonal will be logarithms of the eigenvalues. Now you may say, but if I can take this matrix and it's diagonal, like it's over here, then this trace is just the Shannon entropy of its eigenvalues. Yes, it's true. So for diagonal matrix, S of A is S of rho A. So it means that because the trace is invariant with respect to the unitary transformation, so you can take your matrix, whatever you have, you can diagonalize it and compute just Shannon entropy of this diagonal matrix, and this would be your von Neumann entanglement entropy. This is true. Now, and still, I really want you not to be fooled by the fact that you can diagonalize it and compute Shannon entropy. It's a quantum quantity. The very fact that we cannot characterize subsystem by a vector and need to characterize this by matrix, and then we need to make a trace out of this matrix, is already quantum phenomenon. Okay? That's just this very fact. So in this sense, the von Neumann entropy characterizes non-locality of quantum things, right? And if we happen to work with a system which is in a pure state, then we'll have here in this sum only one term. Then the probability this it will be not a matrix, will be a single entry, and what would stand here is unity, which is a probability of this state B, and the logarithm of it will be 0. So it's as it's naturally, and it's called pure state. So this is a mixed state, and opposite of the mixed state is pure state. So for pure state, S of rho is S of A is exactly 0. But generally it's not. Okay? And so now we may compare it with classical. You remember how we characterized correlation in a classical case? We say that if we have A and B, we can characterize it by a mutual information, which was S of A plus S of B minus S of AB. Okay? Let's apply to our case. Again, I really want to focus you on the fact that my AB is a state. Right? It could be non-factorizable, but it's a quantum. It's not a statistical object. Right? It exists in a single pure state. So AB composite system is in a pure state. It has no analog, right? In a classical case, because it tells me that now this SAB is 0 in a quantum case, right? And now, for example, if I would have A and B completely correlated, in a classical case, I would have S of AB equal to S of A equal to S of B, all generally non-zero, and my mutual information would be equal to the same. In a quantum case, S of AB now 0. So if these are correlated, my I is twice S of A. Again, I don't know simple interpretation of it. Sometimes people say, okay, quantum correlation are stronger than classical. I don't really know what it means. This is just a statement. But what is really more important is that we'll now try to work with this as something which is a purely quantum. It does not have a simple analog with a classical mutual information. And maybe the most bizarre part of it, which we will address on the second part, is that S of A is larger than S of AB. S of AB is 0, and S of A is generally not. So and now I want to show you what I promised is a general or graduate form of uncertainty relation. Incidentally, I don't know if Heisenberg knew this in this form. Not sure. He lived long enough, but so what now I want to do? I want to consider again. You remember what was uncertainty relation is about? Was about one set of orthonormal states X and another set Z, and they were having non-zero projection one into another. Okay? So now I want to do it most generally when we have this state also a mixed state. So imagine that I would have rho. Again, rho always would mean that this is a density matrix which characterizes the. So now I will be measuring it, using an operator mx, which projected on this set of orthonormal state which are x. Okay? But I can also do it by projecting it on this set of states which are z, right? And so now I can say that if I project it on this, this would give me another density matrix, which would be now in this representation. So it will be in terms of state x, and it will be here the matrix element of my matrix projected over here, and this is a sum of x, and I would call it rho x. I can do the same with mz. So now what I want to do the same tricks that we always used in a classical information theory. Namely, I want to consider a relative entropy and use its positivity. Namely, I can say that I can define d between rho and rho x, right? And this would be as a trace rho log rho minus rho log rho x. Just defined like it. And so this would be something which I can say that this is give me a minus, I guess, s of rho, right? So this would give me minus s of rho. But what this would give me is that because I'm tracing everything which is not x out, and this is essentially the s of x. Because after my measurements, I have a probability distribution. And probability distribution of measurement is the usual Shannon entropy of respective measurement which done only on x. So this is then my operator which does projection and measurement on x, and this is the probability distribution related with these measurements. On the other hand, I can say, and what we also discussed with respect to relative entropy, is that I have a monotonicity. Namely, that this d rho x must be larger or equal if I do mz acting on rho between mz acting on mx on rho. This is rho x, right? Which means that if I additionally, so any projection diminish my possible information that I have, right? Because essentially projecting in on z means that I'm losing something out of this x. So generally, this is something which is which has this inequality, and now I need to compute it, which is let me write it in its full glory. So this will be again s of z and minus trace rho z log m z rho x. So it is this quantity which is over here, which essentially I need to analyze. So let me write it separately, what it is. So I am writing a logarithm of mz rho x, and it is essentially mx rho. So it's a long. So first of all, it has this, well, z's on both sides, right? And then it has a sum over x. I need to insert this over here. So it has this x. And Am I doing it right? Yeah. So it will be a projection of zx, x rho x, and zx projection. Yeah. No. That would be xz projection. So again, it's like we did it in algebra. You take this matrix, you project it on one basis, and then you reproject it on another. So you have all this. If I would write it in indices, there would be I, J, M, N, K, L indices, all the sum over it. This algebraic relation, right? So what now I will do with it is that, but I'm doing this orthonormal basis. So these matrices are diagonal. So essentially what I'm doing, it will be a matrix on which my logarithms would stand over here. And but the logarithm is a monotonic function. So when I will take, yeah, where is my logarithm? My log is here, right? So I forgot to put log over here. So I can say that this is less or equal something which I can replace by a squared, namely that I would say that this max over xz, xz squared, and what would remain, it is this sum over x. So what I essentially did, I say that all this sum over different indices definitely less than if I would just take square root of it. But what remains here in this sum is just unity. This is just rho xx, which is just a sum of all probabilities. So essentially what I would obtain, that this is equal to maximum over xz, which was my c in my original formulation xz squared. Okay. So now, because this is larger than this and this is smaller than this, I can write the following relation: sx plus s z larger or equal logarithm 1 over c. You remember the c was xz squared plus s of rho. This is the most general form of uncertainty relation. And let me finish with this and we go for the break. So it tells me that if you are working with a pure state and it's one-dimensional, then this is, and it's which means this is zero. So there is no projection here. This is just one-dimensional. The moment you have in more than one dimension, then generally there is a projection of one basis into another. X and z, they have some projection. It could be unbiased, and then it would be just D. But generally, it could be whatever. It depends on the nature of your state. But if on top of it, you are working not in a pure state, but in a mixed state, then it also involves this purely quantum entanglement entropy, which adds to it. These are classical entropies of measurement, like we had it in the, unfortunately, I've already erased it. So the classical entropies of measurement are bound, and this is just a distribution. So probability of having momentum or spin or whatever are bounded by non-commutativity of two operators, which is essentially a mutual projection of eigenstates of these operators of momentum, and plus the entanglement entropy of the mixed state. Okay? Break. 15 minutes. It's a difficult material, right? But I mean, you still remember your quantum mechanics, but we are now looking from different perspective. Okay, so see you in 15 minutes. And guys, I have a personal thing to ask you. Here I put here, what I'm teaching you is about to be a book, and I have different suggestion of my editor for cover. So if you give me a feedback, which book well, you can say I would not buy your book anyway, but okay, anyway, so just which cover you like more, or you can kind of take your pen and just like say put a plus in which you like, okay, or tell me what you like or what you don't like about them. So they are pretty different in a sense that.